Okay, everyone, quiet please. We are currently trying to schedule another tutorial. I know that there are some people that are having some problems with some clashes, and so they can't get to any one of the tutes. At the moment, we are trying to schedule a tutorial for Tuesday at 4 o'clock. Okay, so for those of you that currently aren't enrolled in a tute, that's what we are currently trying to do. So it probably won't be happening today, but hopefully by next week we will have the venue sorted out. The reason I couldn't sort it out for today was, for some reason, the timetable link, the venues link on the timetable page wasn't working, so I actually have to do it personally. I actually have to speak to somebody, so I couldn't get anybody this morning, so I shall work on that and let you know what's happening with that. All the other tutorials will be running as normal. Okay, now what we gave out today was part 2 of the notes, and quiet people, part 2 of the notes, and also the lab notes, because the labs are starting, of course, next week. So of course you will know better than I who is on next week and who isn't, but labs next week on Monday and Thursday, and this week of course we start the tutorial starting with today at 2 o'clock. And then we've got one tomorrow at 11 and one on Thursday at 9 at this point. Okay. Sorry, down? This thing. This is where I usually snap my fingers off. Da-da-da-dum. Okay, don't call me an engineer for nothing. Okay, let's continue on with where we were at last week. We've got a little bit more of this quantum mechanics stuff to get onto, and it still isn't going to be particularly intuitive. Okay, I expect us to finish this particular section sort of today, tomorrow, and then after that, when we get on to part 2, we still have to deal with quantum mechanics a bit, but it's going to be in a more intuitive sense. It's not going to be in a mathematical sense, so it'll be more intuitive, and hopefully you'll find it a little less hard going. Okay, so we'll start off today with the uncertainty principle. Now, I don't know how many of you have heard of that. Probably you have in physics at some stage or another. Now, essentially where the uncertainty principle comes from is when we talk about quantum mechanics, I said to you that we don't have this definitive, the electron is here or the electron is there. It's not such a deterministic thing. What it is we say that the electron has a high probability of being here or a high probability of being there. And so with that relates some uncertainty. In classical physics, all of your laws are deterministic. We say the particle is here and it's accelerating at such and such an amount, and therefore at time 2 it's going to have a velocity of such and such, and it will be in position such and such. We can't say that anymore. We can say that with sort of large bodies, you know, in astronomy and tennis balls and all that sort of thing, but we can't really do that on the microscopic level. So, can we determine by experiment at the very same instant in time both the position and the momentum of matter or radiation? And the answer is not more accurately than by Heisenberg's uncertainty principle. Okay, seeing as you're frantically writing, I shall give you a little bit more time to do that, and then we shall continue. Now, from Heisenberg's uncertainty principle, he basically said that we can only measure with a certain amount of accuracy the position and the momentum of a particle, and the uncertainty related to it is going to be greater than some constant. We'll talk about that in just a moment. Something I need to point out to you, though, is that with the uncertainty principle, it's not because when we measure something we disturb the system. That's something that you read in a lot of books, and they say, well, you know, it's because you're observing it, that's why you can't get, you're changing the system and you can't get an accurate measure of things. That's not true. The reason for the Heisenberg's uncertainty principle is purely because of the probabilistic nature of your particles. Okay? It is not due to the fact that you have poor instrumentation or the fact that you're observing the particle that causes the uncertainty. It's entirely due to the wave nature of our electrons or our particles. Okay, so having a look at what the uncertainty is, the way we can state it is to say the uncertainty associated with the position of our particle times by the uncertainty associated with the momentum has to be greater than or equal to h bar over 2, or h over 4 pi, where h is Planck's constant. Okay, so there's a tiny little bit of writing here, and I'll continue on in just a moment once you've written that down. Okay, so when does the uncertainty principle actually play a part in what we're doing and what we're thinking? When does it actually matter? Now, we're going to do a couple of examples just to show you sort of the orders of magnitude that we have associated with the uncertainty principle and certain situations. So let's just rearrange our equation. If we start off with the uncertainty with x times by the uncertainty with momentum, we know that momentum is written as m times by delta v. That is the uncertainty relating to velocity. So that m isn't going to change, so we can put that on the bottom line over the other side. So we end up with the uncertainty of position times by the uncertainty of velocity is greater than or equal to h over 4 pi times by m. So what this means is that as the mass increases, the uncertainty decreases. Okay, so when you start getting to larger particles like a golf ball or a tennis ball or whatever, it doesn't really matter so much, okay, because the dimensions of your particle or your object are getting to the point where the uncertainty principle is of little consequence. It's only really going to play a part when we start talking about electrons which have very low masses, etc. Okay? All right, let's have a look at a couple of examples. And let's just start off with a nice simple one. We've got a mass of 1 kilo. And we're going to compare it with the uncertainty associated with the mass of an electron, which is 10 to the minus 31 kilos. If we have a look at this, we've got the uncertainty of x times by the uncertainty in velocity, h over 4 pi m. Sorry, there's a correction just there. I've written 2 pi m. It should be 4 pi m. So I've got h, which is 6.62, 10 to the minus 34, divided by 4 pi. We end up with 10 to the minus 34. Now you might think, well, you know, is that significant or not? Well, if you had a mass of 1 kilo, you can imagine this thing is going to have reasonable dimensions. You're not going to end up with a microscopic particle that is 1 kilo. You're going to end up with something that's of reasonable visible dimensions, and so therefore whatever change in position or change in velocity, uncertainty in position or uncertainty in velocity you're looking at, it's going to be insignificant compared to the dimensions of your 1 kilo object. However, if you do the same calculation with an electron, it turns out that the uncertainty, the two uncertainties multiplied together, is something of the order of 10 to the minus 4. Now you think, well, 10 to the minus 4 is still quite small. It's not as little, obviously, as 10 to the minus 34, but it's still quite small. The thing is, the dimensions of your electron are going to be extremely small. Okay, they're going to be extremely small. So any small difference is going to be significant because you're going to have the dimensions of your electron, say, being of the order of less than an angstrom, okay, less than 10 to the minus 10. So any delta x is still going to be significant with respect to the size of your electron. Okay? Now the next example actually illustrates this in a better way. Okay? This time what we've got is we've got the speed of a bullet of mass of 50 grams and of an electron, which has got a mass of 10 to the minus 31 kilos, are measured to be the same. They're both measured to have a velocity of 300 metres per second. Okay? Now, the uncertainty associated with that velocity is 0.01%, so 1 10 to the minus 4. So with what accuracy could we determine the position, i.e. delta x, or the uncertainty of x, what accuracy could we determine the position of each if we measure the position simultaneously with the speed? Okay. Let's have a look at what we get with an electron. If we have, let me go through this with you and then you can write it down. If we have our momentum, which is equal to m times by v, okay, so we've got the mass times by the velocity gives you some quantity. We then say delta P is equal to m times by delta V. So therefore we end up with that quantity being 2.7 10 to the minus 32. So there's our uncertainty, and this is what the uncertainty is associated with. It's associated with the velocity, but it's going to be as momentum, of course. So uncertainty of x times by uncertainty of P is greater than or equal to h over 4 pi. We can rearrange that to be uncertainty of x greater than or equal to h over 4 pi delta P. We know what delta P is equal to because we just found that, and it turns out we've got an uncertainty in position of 0.2 centimetres. Now if you consider how small an electron is, 0.2 centimetres is massive. Okay, that is a massive uncertainty, because remember when we were talking about the Bohr radius, okay, we had our positively charged nucleus and then we had our electron and it rotates around, and we said that the very first radius that we've got is 0.5 angstroms, didn't we? So you can imagine 0.2 centimetres is massive. Okay, the uncertainty associated with the electron position is huge. Okay, let's compare that to the next one, and I will give you some time to write this down, so don't panic just yet. Okay, so that's about 10 to the 7 times the diameter of your atom. Let's do the same thing for the bullet. We have a mass of 50 grams multiplied by the velocity. We find our delta P, which is going to be our mass times velocity of 15 times by the uncertainty to give us 1.5 10 to the minus 3. If we then plug that into our formula, what we have is that delta X is going to be of the order of 10 to the minus 32 metres. Now you know with your bullet you can see it. If I rotated, no. You can see it, you can feel it, you can touch it, meaning that it has very obvious dimensions. It's going to be a couple of centimetres by maybe half a centimetre wide. That 10 to the minus 32 metres is not going to be significant. Okay, so you can see the uncertainty principle only matters for little particles. Okay, I'll give you some time to take down what we did just in that beginning part of the example. Your velocity would be bigger indeed, but you've still got, if you work it out, it turns out that delta x is still going to be significant. I actually had a thought of... In this particular case, no, but in, like, just say you were talking about thermal velocity and you said, okay, you know, you've got your velocity uncertainty is going to be, instead of being 10 to... That's right, but you're still going to have the uncertainty, it's still going to be very large, yeah. Now, I actually had to think about that. I went for a walk this morning and thought, did I think that one through? And yes, I did. But it's a very good question. Yeah, it can't compensate enough. Okay. Okay, quiet people. Hang on. Second line, yes, sorry, I forgot to expand that one up. What it says is this line here. Is that what you're looking at? Okay, so it's delta P is equal to M delta V, which is equal to 10 to the minus 4 times by 2.7 10 to the minus 28, which is equal to 2.7 10 to the minus 32. Yes? Yes, but it's M delta V. We're looking for the change in the entire thing. Okay, so it has to be with both of them because the formula relates to it. You're going to put M in there somewhere, and whether you put it in here or you put it into the next bit down here, it makes no difference. Okay, so I would either put it in up here or I'd put it in down here, and it will come to the same thing. Okay? Don't worry, I do know that this is not an easy thing to get through, okay? Okay, sorry, what have you got in your notes? Anything is possible. Okay. Oh, okay. You know what I did? I remember now. I actually forgot to put in the velocity. Okay, the velocity term was accidentally missed out of that second line for the electron. Okay? In your notes there is a correction. I'm very sorry. There was a correction in your notes. Okay? So what I have written up here is correct. What is in your notes needs to be corrected. I forgot the factor of V. But the final result is correct. The 2.7 10 to the minus 32 is correct. I just forgot to write in the number 300 in there. So apologies for that. Velocity. Mass times by delta V is the uncertainty associated with the velocity. Okay, folks, we have another one of these to do. Can I take this away now? Has everyone got that? Okay, let's just go to the last of these uncertainty examples. This is just using the other of Heisenberg's uncertainty principle, which I usually forget to do. But the other one of his relationships is delta E, that is the uncertainty in energy times by the uncertainty in time is greater than or equal to h bar over 2. Now, in this particular one, just let me explain to you what it is, because inevitably you will ask me what's going on. We've got an electron and it is going between two states, okay, and what we know is we know the lifetime associated with each state, okay. Now, we're going to substitute in the lifetime for delta T. And you might say, why? There's no delta, there's no change, there's no nothing. All it's saying is that the electron can disappear, i.e. it can move to the lowest state any time up to the lifetime. So perhaps it might move from this state up here down to this state down here at time is equal to 0, but the longest it's going to live is this number up here, okay, or the average. It's actually the average it's going to live, but we will take our delta T to be, well, that's going to be the maximum and the minimum is time is equal to 0, okay? So that's what is happening here. Now, what we do to work out the uncertainty in energy is we work out the uncertainty in energy with respect to the first energy level, and then we work out the uncertainty in energy related to the second energy level, and we add the two uncertainties together. Okay? So that's how this problem is being done. I didn't really go through all the steps when I worked it out. So, delta E times by delta T greater than or equal to h bar over 2. So I'm going to put the delta T on the bottom line. In the first case, for the first excited state we talk about, delta E is calculated as h over 4 pi times by delta T. The number turns out to be 10 to the minus 27 joules, which I can then relate to being as 1.4 10 to the minus 8 electron volts. Remember to go from joules to electron volts. I divide by Q. Okay, so I just divide by Q, which is 1.6 10 to the minus 19. Now, looking at the uncertainty associated with the second energy level, again, I have h over 4 pi delta T. Plugging in the various numbers, I then have 4.4 10 to the minus 27 joules, and then however many electron volts, 10 to the minus 8 electron volts. So the total uncertainty associated with the energy will be each of these added together to give me 4.17 10 to the minus 8 electron volts. I would not expect you to know that intuitively for an exam or anything like that. Okay? If I were going to give you a question, I would make it a much, much more obvious one like the previous example. Okay? So I don't think that this is an innately obvious one, but it was one of the few examples I found that related back to energy. Okay? So I wanted an example of energy in there for you. Just want you to know that this is probably the hardest that my half of the lecture course is going to get, okay? After this, hopefully it will get easier. Okay, when you finish taking that down, if you could just turn to the next page. I needed to remember to go to page 49. That's 49 in my notes, but your next page will be page 35. And we shall have a little talk about Schrodinger's equation. As you might have gathered from the numbering of the pages, I've written a large amount of stuff, but I've shredded it down to the minimum that I think that you can survive on. Okay? So it is the bare bones of what you need, I think. Okay, let me just talk to you a little bit about this first, and then I'll give you some time to write down. We all know about the dual nature of light, behaves as a particle, behaves as a wave, and then we talked about the dual nature of matter, i.e. our matter obviously behaves as particles, but it also has a wave-like nature. It would therefore seem reasonably logical to some that the governing equation for matter should probably be a wave equation. Okay, if it has a wave-like sort of character to it, a wave equation would seem logical to describe the motion. Now, we are not going to go through the derivation of Schrodinger's equation. What's amazing about Schrodinger's equation is he didn't use any assumptions or anything like that. He just came up with this equation, just working through regular wave equations, and came up with his equation, which then describes everything that you would need to know about a particle in a given system, which is a pretty amazing thing. Now, the form of Schrodinger's equation looks like this. We've got our minus h bar squared over 2m, so that's just a bunch of constants. Now, have you guys come across this sort of thing in maths yet? Yeah? For those of you that haven't, these are partial derivatives. What we do is we take the second derivative with respect to x of a particular function, and we add it to the second derivative with respect to y of that same function, plus the second derivative with respect to z of that same function. Now, I think that this is called del squared. Okay, it's a Laplacian operator, and it's a very well-known one, and one that you will see in a lot of books. And if you haven't come across it in maths, you will do so shortly. Okay, we then add that to the potential energy times by this wave function, which is equal to, we've got a complex operator here, h bar, and then we've got the partial derivative of our function with respect to time. Now, this describes everything we need to know about the particle. Now, it's a shame we can't solve it. No, not really. We can solve it for very simple situations, but overall it is a very difficult equation to solve for complex atoms, etc. Now, in terms of what do you need to know? All I really need you to know is that this equation exists, okay? That you can also see it in this form down here. Now, this is called the time-independent form of Schrodinger's equation, and what it is that they've manipulated it and moved it around such that we get rid of time. So all we have are the space coordinates, x, y, and z in there, but we don't have any time in there. Okay, so that's pretty much all I really need you to know about this. We aren't going to be doing any solving of this equation. What we will do is we will say, here is a situation, and as it turns out, the energy of that situation calculates out to be this. We are not going to derive it. All we are going to do is we are just going to look at the results and say, well, isn't that nice? Okay? Because what we will be doing in part 2 of the course is looking at this in a more intuitive fashion, and we will show that some of these results, here is where this result comes from. Okay, that's how we're going to be treating Schrodinger's equation. Okay, just one other variable in here that I haven't said. This is E, this is the total energy of your system. Of course, V is your potential energy. Okay, now, the significance of the Schrodinger's equation, like I said, is it describes everything you need to know about a particle in a particular situation. So you might be trying to describe where is an electron in an atom of hydrogen. Okay? So we can put in our parameters for potential energy or whatever it happens to be and end up with some solutions to that. Now, in terms of where can we actually get something vaguely useful, from our point of view where we don't know a lot about quantum mechanics, what can we sort of get that's useful out of there, is that this Schrodinger's equation can be solved. And what you find is this term here. And this is just our wave function, and it's called psi. Now, if you get psi and you get the intensity of this function, what it gives you is the probability density of that particle. And you might say, well, what does that mean? What it gives you is it gives you a shape of the probability of finding an electron in a particular region of space. Okay, and you might say, well, it still doesn't mean anything. If you go back to your Bohr model, right, and we have our positively charged nucleus, we have our electron rotating around it. If you were to look at the probability density of this electron as it rotates around, and note that it can move out of that first radius, it might go to the second radius or the third radius, it might move further out as it gets more energy, you would have a probability density that would say, okay, it's going to be non-zero outside of that first radius. So supposing you have your particle here and it can shift into all sorts of different positions, you might have, well, it's most likely to be at this position here, but it has a non-zero probability of being further out from there. Okay, that's what this function more or less can give you. So you get Schrodinger's equation, you would solve it for the given parameters, you would get a wave equation called psi, your wave function. This wave function you would then find the intensity of that to produce a probability density. Okay, now I've actually got this written on the next page, but it's even messier than I've got it written here. Okay, I'll go back to the top of that page in just a minute. Okay, so like I said, the significance of Schrodinger's equation that describes the location energy of an electron, taking account of all the system parameters. The solution of Schrodinger gives you your wave equation, which has no physical significance on its own, but if you find the intensity, i.e. the amplitude of this function, this will give you the probability density, i.e. the probability of finding our electron in a particular, or particle in a particular region of space. We will come back to this amplitude thing a little bit later on. Okay, I might as well go through the limiting postulates and then we'll go back to that beginning of that page. Okay, so the wave function needs to satisfy these various criteria. The reason I'm giving you this is you may be using this in the second half of this course. Okay, so just for completeness, that's why I'm giving it to you, but we will not be using it particularly ourselves. So the wave function has to be single valued for R and T. You might wonder what R is. R relates to all of the spatial variables. So it's basically X, Y, and Z in some form or another, but we're not going to worry about that. But that's essentially what R represents. It's looking at X, Y, and Z, all of the spatial variables. We also need to we need to be able to find the intensity of our function, so it's normalizable, and it's finite, and all of the probabilities that you get are less than or equal to 1. You will not get a probability of equaling 1, in fact, because that goes against the whole quantum mechanical thing of saying the electron or particle may or may not be in a particular position. We have to say it's got a probability of less than 1, in fact, but that's the way it is stated in most books. Okay, so the reason it has to be finite and the probabilities less than or equal to 1, the particle has to exist somewhere. Okay? And finally, a real maths one. Psi and the first derivative are continuous, except where the potential has an infinite discontinuity, of which we don't have to worry about any of that. Okay, I shall go back to this page here because there was a tiny little bit that you may wish to write down. Thank goodness we're going to finish all this rotten stuff tomorrow. Yes. I don't know. Okay, it's only been solved for very limited cases. So I don't actually know. I don't solve it. I don't actually use Schrodinger's equation. I've never used it in my life. So, but apparently, sorry? Yeah, it's probably a good thing. I can still smile and think life's okay. Okay, I'll just move this up slightly for those of you that wanted to take down any of those diagrams. Is anybody on that page still? No? Okay, let me move over to this page. Quiet, folks. I know this is yucky. Oh, gee. We've got the hydrogen atom, and we've got potential wells, and we've got free particle. Excellent. Okay, looks like everyone's finished that. Let's continue on with this torturous topic. Okay, here's one with mainly just like words in it, okay, so it can't be that bad, can it? Right, when we have Schrodinger's equation, we solve it for the wave function psi. Now, what do we do with the wave function? Well, we know this whole thing about we don't know exactly where the particle is, so we don't exactly know what all the values are going to be, yada, yada, yada. What you can do is you can come up with an average value, and these are called expectation values, a value that you think that the solution is going to be, or that the electron should have, or the particle should have, and these are just called expectation values. There is a mathematical formula associated with it, but we are not going to deal with it. I just want you to be aware that that's what they're called, that's what they relate to, and perhaps you will be doing it in the second half of the course. I do not know, but at least you know what they are. In terms of how do we actually find some of the quantities associated with our particle, the main quantities that we want to find are position, momentum and energy. Okay, position, momentum, energy. So how do we do it? Well, generally speaking, dealing with Schrodinger's equation can be a bit of a pain. So what we have are things called operators. Now, operators is just a mathematical term, and what it basically relates to is we will perform this operation on the wave function, okay, psi that we have. A wave function, an operator can be a number of different things. For example, if we've got our del squared, that's what I'm going to call it. This is an operator. We know that we take the second derivative with respect to x, y, and z, and we sum them together, and that's the operation that occurs. We have something called a Hamiltonian operator, and this makes the Schrodinger equation simple. Okay, and what we end up with is we can say that if we have the Hamiltonian operator operating on the wave function equal to total energy times by the wave function, we end up with Schrodinger's equation. Okay, isn't that very exciting? So now you know. Now, operators can be quite simple things, of course. It can be something like, if you're just looking at the cube root of a number, that also is an operator, just the cube root of something, the square root of something. All of these things are operators. They're just saying, perform this on the function. Now, here's another thing that you will just merely look at and say, oh, how nice. The quantities, as I said, that you want to work out in quantum mechanics relating to a particle are mainly the position, the momentum, and the energy. And what you can do is you can use operators to operate on the wave function to produce these quantities that you're looking for. Okay? As I said before, we will not be doing this ourselves. Okay? We will not be doing this for my part of the course. And all I need you to be is just aware of the fact that these words exist, as far as I'm concerned. Okay? Lordy Linya. Let's have a look at... Okay, what we're going to have a look at now, and is the sort of like finishing off section of this, is just different situations that we have. I know that it seems like a very circuitous route to get us getting our model of our semiconductor. Okay, we are getting there, and in fact by this time next week you will probably have a fair idea of a reasonable model for a semiconductor. Okay, so we will get there. What we're going to have a look at now is we're going to take different situations such as a free particle. We're going to have a look at a particle that lives in a potential well, and we're going to have a look at hydrogen, and we're going to see what Schrodinger's equation pops out. We're not going to be doing any derivations or anything like that. We're just going to see what the equations are that pop out. And why we're going to do this is because next week when we have a look at the more intuitive way of treating this, you will see that the equations do in fact match. Okay? Let's start off with a free particle. And just to remind you what your free particle is, it's when you don't have any fields or anything like that acting upon your particle. You can think of an electron in a metal as being a free particle. Okay, so it's free to wander around the material. Now, the potential energy that we have is equal to 0, so therefore Schrodinger's equation, we just get rid of the V. And here's one I prepared earlier. The solution to that turns out to be A sine this quantity here to the square rooted times by X. Note that this is just a one-dimensional form of that solution. Okay, this is just one-dimensional. Okay. In most cases, you'll find the solution to Schrodinger's equation will be of the form of either sine or cos, or a combination of sine and cos. Now, you might wonder why. But when you think about it, if you have a second-order differential equation, when you differentiate sine, it becomes cos, and when you differentiate that again, it becomes sine again. And you know that with Schrodinger's equation, it's such and such plus such and such is equal to 0. Okay, so what we need is something with the second derivative is going to look not that dissimilar to something that was the original function, so that it equals to 0, right? So therefore, usually the solution looks something like sine or cos, or sine and cos, okay, so that they tend to cancel out. Okay, just the quantities that pop out. E, I've written kinetic energy in your notes. It should say total energy of the particle, mass of your particle, and Planck's constant. We're going to be looking at this again in part 2 of the notes. Okay. This is all just, related to the limiting postulates. The solution is permitted as long as we have the energy being positive. We can't have this being the square root of a negative number because it doesn't fit all of the postulates, etc. Sine is a single-valued, finite and continuous, so we've fulfilled all of the bits and pieces relating back to the wave function. What this also says is that the energies associated with a free particle are continuous. And when you have a free particle, the energies are continuous. If you think about, say, back to the photoelectric effect, okay, the energies that your particle can take on is in fact continuous, okay, and that's what you've got here as well. Okay, I've tortured you enough. Tomorrow will be the last day of bad stuff and we'll get on to some good stuff. That's the... So, yes. Yes, that's exactly what I was saying. It's sine plus cos, because that's a form of...
Oh, the exponential.
But yeah, it does. I accidentally added in some stuff that shouldn't be in your notes, and it's one of those things that, yes, that's what that stuff is. Hi.